Question 3. The diagram below shows a cross-section through a current-carrying solenoid. The current is moving into the plane of the paper at the upper edge of the solenoid and out of the plane of the paper at the lower edge. There is a vacuum in the solenoid. So C1, sketch lines to represent the magnetic field inside and at each end of the solenoid. Now, we are looking at the magnetic field. Now, this is caused by these currents. Now, we use the right-hand solenoid rule where we put our fingers in the direction of the current in the solenoid. So it's actually going to be the fingers come out at the top and they go in at the bottom. So the thumb actually points towards the right, and that is the direction of the magnetic field. Now, in drawing this magnetic field within the solenoid itself, you've got a uniform magnetic field. So that must be shown by the magnetic field lines. So you need to use a ruler when doing this. I'm not going to use a ruler, but you need to use a ruler. Firstly, draw a center one right through. I'll draw one right through the middle like that. That would be in the center. And then on each side, now you need to make sure that the spacings of these are the same. So I'm just going to go something like this on either side. They should be evenly spaced like that. They shouldn't be crossing each other. And then what happens is that they diverge out like that. And it's a symmetrical situation. So you should try and get these sort of the same. Hopefully you'll do better than me. Now the direction of the magnetic field is in that direction like that. So because they are straight and they're evenly spaced in here, showing it's uniform, as you get towards the side, because you're getting the spread out here, you are getting that it is no longer uniform as you go out. So something like that would be your diagram. Then it says an electron is injected into a region of uniform magnetic field with a flux density of 4 millitesla. The velocity of the electron is 1.6 times 10 to the 7 meters per second, and an angle of 35 degrees to the magnetic field as shown below. So we've got that. We've got here's the direction of the magnetic field is in that direction, and we've got our motion is in like that of our electron. So it's determine the component of the velocity of the electron normal, that's 90 degrees, to the direction of the magnetic field. So we're looking at this component there. So to find that, obviously, this is our hypotenuse. This is our opposite. So we're going to use sine of 35 is equal to opposite over 1.6 times 10 to the 7 meters per second. And we're going to multiply that out. And we get, when we do that, we get our opposite, which is our velocity in the vertical, I'm going to say velocity in the y direction, of 9.2 times 10 to the 6 meters per second. So this is your velocity that is going at 90 degrees to the magnetic field. So that's your velocity in the y direction there. Then describe, making calculations where appropriate, the motion of the electron due to the component of the velocity. So with this component, we've got our velocity is at 90 degrees to the direction of the magnetic field. There will be a force that will be on this at 90 degrees. So it's actually going to cause circular motion. You're going to get circular motion. We could work out the force. The force will be given by this. Now, because it's 90 degrees, we're looking at that component. That's equal to 1. So the force is equal to Q, which is 1.6 times 10 to the negative 19, times our 9.2 times 10 to the 6, times our B, which is 4 millitesla. So it's 4 times 10 to the negative 3 Tesla there. So that would be the force. Now, we know that when we are looking at the radius for that circular motion, we can use our circular motion formula that force is equal to mv squared over r. So in looking at our r, we're going to get mv squared over our force. So this would be 9.1 times 10 to the negative 31 times our velocity squared. Now here, as we've worked out above here, we can maybe just simplify this down here. We're going to get our force from that is QVB, so we can cancel out one of those V's there. So it's going to be times 9.2 times 10 to the 6 divided by, that's equal to 1.6 times 10 to the negative 19 times 4 times 10 to the negative 3. Now when we work that out, it works out to be about 1.3 times 10 to the negative 2 meters. So it's about 1.3 centimeters. So we have circular motion with a radius of about 1.3 centimeters, and the plane of it is in the plane 90 degrees to the page. All right. Now, just to go a little bit further on this, I want to discuss this a little bit further. The actual motion of this would actually be into a spiral because you've got this horizontal component. So let me just take this out here. You've got this horizontal component. So you've got that component which is in the horizontal, and that component in the vertical. So you're going to get this type of motion here. You're going to get something like that. This direction over here will be your horizontal component. This velocity in that direction will be your horizontal component, say your Vx. And this would have a radius here. It would have a radius there of, I think we said it was 1.3. 1.3 centimeters. And the particle. So it would be like in a helix, a spiral that it would go.